Hello everyone and welcome back to my channel. In the past two videos we talked about the forward and backward difference scheme to understand how the finite difference schemes work. And today we are going to take a slightly different blend of these two methods so that we can try to understand that how can we obtain a little bit more accurate differencing methods. I tried to give you some glimpse of this in the past lectures. So if you haven't watched the past video, I would recommend you to watch that. But in the class today, we are going to consider what is called as a central difference scheme, and which is, I think, the most widely adopted method because of its simplicity and accuracy. So that would be the most hot topic for the today's lecture, and I hope that you would appreciate that. So without wasting any further time, let's get started. So in the first class, we looked at the forward difference method and we saw that the truncation error for this scheme was of the order delta x, where delta x is our grid spacing. The same idea holds true for the backward difference scheme, which we saw in the last lecture. And the motivation behind wanting to go for the central difference scheme is to look for some stencil that can give us even smaller truncation error. So to understand how the central difference scheme can be obtained for the first derivative of a function, so it is important that we are seeking the approximate to the first derivative. That is, if we are given a first derivative, it could be a partial derivative, it could be an ordinary derivative, but as long as it's first derivative of a function, how can we approximate it numerically? And that is what we are going to see today using the central difference scheme. So in order to understand how we can obtain the central differencing scheme formula, what we can do is we can look at this particular expression, which is nothing but the Taylor series expansion. So what I'll do is I'll try to take this entire expression over here and I'll just copy it. I'll paste it on my new page so that we can see how to go about it. So this is the same expression that we used for the forward difference approximation, and the same thing we do for the backward difference approximation. I take my Taylor series expansion, I put it on a new page over here, and what we can observe that both of these terms, they have the first gradient coming in, and previously we used these equations independently, and now what we want to do is we want to just algebraically manipulate these equations. And if I simply subtract the bottom equation, that is the equation for the backward differencing, from the top equation, we can see that this negative would simply become positive. So I'll just rewrite some of the signs here. So this becomes a negative, this becomes a positive, this becomes a negative, and this becomes a negative as well. This is a general term, so you might have to write this expansion a little bit more to understand what kind of terms would get cancelled out. So for example, the first term on my right hand side, that would be cancelled out. The second term is going to retain itself, and similarly if you would observe, then the third term may get cancelled out. So I'm just cancelling it out for now, and I'm putting an exclamation mark because it is valid if the grid spacing is equal. So this is valid if xi plus 1 minus xi would be equal to xi minus xi minus 1. So as long as the grid spacing is uniform, we can cancel out that term. But if the grid spacing is not uniform, then this term may not be 0. The difference of these terms may not be 0. But for the simplicity and for get you to understand how this numerical methods work, let's try to take this as 0. So if we go out here and we subtract this, on the left hand side we get phi of xi plus 1 minus phi of xi minus 1, and over here what we can get is it would be 2 times, assuming that the xi plus 1 minus xi would be equal to this particular quantity, and I'm just going to represent it using a delta x. and this becomes del phi over del x at the I. And the next term that we would have for this particular expression would, I think, be of this particular form over here. So it would have delta x raised to power 3 over most likely a 3 factorial combined with a third derivative of phi at the point I, and so on. So I'm not going to write all the terms because my main agenda is to find out what would be the truncation error for this particular scheme. So we don't have to write all the terms, we just need to write the terms enough so that we can understand where to end it. And to do that, what I am interested in is this particular term. So I can bring out the terms on the other side of the equal to sign. So what I may end up getting is that this del phi over del x at my interesting location I, or the index I, would be phi of xi plus 1 minus phi of xi minus 1 divided by 2 delta x, and my first term that remains on the other side would be delta x raised to power 2 over 3 factorial. I think I'm doing it correct. If not, please let me know in the comments if there are any algebraic mistakes, which may happen. So now if you recall our past discussion, when we write this entire infinite series in this form, that on the left hand side we have the gradient or the derivative that we are looking for, and on the right hand side we have one particular term which becomes our approximate to that derivative, and everything else is the truncation error. And usually we are interested in the first term of that truncation error. So let's try to see what that is. And if I use the previous notation, so this is my approximate to the derivative, that is the first derivative that we are interested in, and this is my leading order term for the truncation error. All right, so the final expression according to the central differencing scheme, which is probably one of the most widely adopted scheme as long as the first and second order derivatives are concerned, and the approximation is, I should use an approximation sign here, it says divided by 2 delta x. And if you look at the leading order term, so I'm just writing as leading term for the error, this is approximately, and I'm taking the magnitude of that, so this becomes delta x square over 3 factorial, and it's a third derivative of, but usually we are interested in what is the power of delta x that is associated with it, and for that reason we can say that this is of the order delta x square. And that is a very crucial and very important difference between the schemes that we looked at in the last two lectures. Those schemes were accurate up to order delta x. That basically means they were first order schemes, since the power of delta x was 1. In here the power of delta x is 2. It's quadratic, so it's a second order accurate scheme, and we will see very shortly through a very simple example as to how that actually comes into practice. So here the takeaway is that the expression that we are interested in to evaluate the first derivative is this one, and the order of error that is associated with the derivative is delta x square, or it's the second order accurate method. So this is the primary takeaway from this class, that this is how you can derive a second order accurate stencil or a second order accurate method using a central differencing kind of stencil, because here we want to evaluate our derivative at this location I, but we are taking information from I minus 1 and I plus 1. So we are taking information from the neighbors to give you a derivative at the central point. So that's how the naming convention got into this. So this is I hope that this part would be clear. In case if you have any questions, you can write it down in the comments. So before taking the example for you to understand this, I also have one very small announcement to make, that I am going to restart one of the lecture series on CFD that I had delivered about last 2 years ago as well. There was very good response to that. And if you're someone who is starting out in CFD or the problems in heat transfer, and you want to understand how you can write your own solvers to solve a wide variety of problems, this could be a very good starting point for you to start for it. So if you're interested for that, I'll put a link in the description for a Google Sheet where you can fill in your details, and then you can join a WhatsApp group where I'll share the link for a demo session. It is totally free. You can come to the demo session. You can try to understand a little bit more about what is the overall idea of this lecture series and whether you think it could be beneficial to you or not. So now we will take an example to understand slightly better as to how these differencing scheme will come into the picture. So let's take that one. So for the example, I'll consider a very, very simple problem. Let's say that f of x is given as x square, and we are interested to know what is f prime, or the first derivative of this function at x equal to 1. So we know that it's very simple to evaluate that. If we take the first derivative, it becomes 2x, and the correct value, or the right true value, is simply 2. So now let's try to understand how we can use these different kind of schemes. So let's say this is my x equals to 1, and we can consider h as 0.1, where h is nothing but delta x. So I'm having a grid where this is my x equal to 1. Then this point becomes x equals to 1.1. That it is, you can think of this as xi, this is xi plus 1, and this point as xi minus 1, and the value of x would be 0.9. Now if I use a forward difference method, what I'll end up getting is, I'll write in the way that we have looked at in the class. So it becomes df over dx at the point I, it is equal to f of I plus 1 minus f of I divided by x of I plus 1 minus x of I. So it becomes 1.1 square minus 1 square divided by 1.1 minus 1. So if you will evaluate this, this will come out to be 2.1. So this is the way in which we take the grid. That is, we assumed that the grid spacing is 0.1. You can take any grid spacing. Generally, it is recommended that it is less than 1 for these differencing schemes to work well. And if you can take any other grid spacing of your choice, here we took delta x equals to 0.1. And what that essentially means is that the next point is exact 0.1 distance away from the previous point, and so on. So if this is my 1 and the next point is over here, it would be 1.1, and the next point over here would be 1.2. If you want to make it finer, the delta x could be taken as slightly smaller. So with the forward differencing method, we get the derivative as 2.1. It's not the true value. The true value is 2. So that's the error that we are talking about. So in this case, we get approximately 5% error. You can try the same thing with the backward differencing scheme, see if you get the same kind of error, and that could be a very small exercise that you can do. But what I want to show you is that using the central differencing scheme, we can actually get slightly better estimates in majority of the situations. So for the central differencing to work, so for the central differencing method, we have just seen that df over dx at the I location, it would be f of I plus 1 minus f of I minus 1 over x of I plus 1 minus x of I minus 1. So this becomes 1.1 square minus 0.9 square divided by 1.1 minus 0.9. And when you'll do the calculations here, you will get that this is exactly 2. So this is very simple function over here, and it's a coincidence that this central differencing approximate is exactly equal to what we get in the as a true solution. And this is usually true if your functions are very simple, but when you get into more complicated function, you may not see exact replication of your true values. But this is a very simple example to show you that the central differencing scheme is generally more accurate, because in this case, as you can see, it produced exactly the true value. But in the case of forward differencing method, we had approximately 5% of error associated with the value that we calculated. You can take different kind of functions. You can take some trigonometric functions, and you can take different values of delta x for your practice. And you will see that this kind of notion would hold true for a lot of cases, that your central differencing would be more accurate than a forward or the backward differencing scheme. And mind you that all of these schemes are using 2 points only. It's just that the central differencing is using the points on either side of your point that you're interested in taking the derivative on. So I hope that you might have learned something useful in this lecture. These are still very, very simple approximations to the derivative. In the future classes, we would look at slightly more generalized methods. So for example, if you want to calculate even higher order accurate gradients based on these differencing scheme, how you can do that. Or if you want to calculate gradients of even higher order, so for example, second order derivative or third order derivative, then how you will use the finite differencing schemes for that. But today's class is probably one of the most useful outputs, because central differencing, especially for the first and second derivative, is very, very prominently used in the problems of fluid dynamics and heat transfer. So if you understand how to make it work, you would be having a good time while you would be writing your own codes. And if you want to learn more about it, do check out the link in the description, so that you can understand the kind of courses that I'm planning to have in the upcoming days. In any case, if you have any questions, please feel free to write down in the comments. If you like it, I would appreciate if you can just take your 1 second and hit the like button. I will see you in the next class. Bye bye, and thank you so much.